Hello, I welcome you all. The problem reads, cartons having a mass of 5 kg are required to move along the assembly line at a constant speed of 8 meters per second. Determine the smallest radius of curvature row for the conveyor so the cartons do not slip. The coefficient of static and kinetic friction between the carton and the conveyor mu s equal to 0.7 and mu k equal to 0.5 respectively. This problem is coming from the Engineering Mechanics and Dynamics, 14th edition by R.C. Hibbeler. So first things first, let's draw the free body diagram. So I think we can draw the carton. There we go. So this is our carton. It has some weight, even weight, and it has the normal force. Right. So we do not want the carton as it moves in this curve to slip in this direction. We don't want it to slip in that direction, right? So it means we need some friction in that direction, right? We need some friction in that direction. All right. So our friction will be in this direction, like so. Okay, this is our friction, and then let's draw. Let's say this is our center of z-axis, so that we have our row. This is our row. Let's call this our row. So this is our row, right? What else? This is our w. This is our friction. This is our normal force. Now the question here is, and then let me also draw before I talk about this question. Let me use this line. I draw, this is my coordinate n. Okay, so now the question here is, what friction are we talking about here? Are we talking about kinetic or static? Let's look at this particular problem. This box is rolling, okay, or it's being moved as the rollers are going round, right? So we are being told cartons are required to move along the assembly at a constant speed of so this box is moving at a constant speed of 8 meters per second, right? So the rollers are the ones that are moving, okay, and the box, okay, the box is moving in that direction, right? So the rollers, as the rollers rotate, the box moves in this circular motion. But for the box to move, there has to be friction between the rollers and the box, right? So right now, the box in this direction is experiencing, as it is moving, it is experiencing kinetic friction, right? In this direction, okay? Of course, there is kinetic friction in the opposite direction. So this is the movement. This is the movement in this direction. And then we have kinetic friction in that direction, like so. Okay, opposing the motion, because if the box and the rollers were smooth, then even if the rollers are rotating, the box won't move because they will just be slipping, right? And you don't want that, right? So there has to be some friction between the box and the rollers, all right? And this friction is kinetic friction, as the box is in motion. But we want this box not to move. We don't want it to move in this direction, okay? We don't want it to move in this direction. So to prevent it from moving in that direction, we don't want it to move in that direction, okay? So this is the motion, and this one here is the motion. So to prevent this, we need some friction in this direction, and this friction, we are saying, because we want it to maintain this position, all right? Therefore, this friction is going to be the static friction, so that it remains in this position, right? So to prevent this motion in that other side, we need a static friction, and this is the static friction that we are going to use here, right? Is that okay? So the static friction here is the one that because we want this to remain in this position without moving. Therefore, to prevent that, we need some static friction. But along this direction, kinetic friction, along the curved direction, kinetic friction is there. All right. But along this direction, we need static friction, right? Right. So this is what we need right now, right? So this is just equal to mg, and is equal to 5 kg times 9.81. This one is equal to mu s n, and is equal to 0.7 n. Okay, so this axis here, this axis this is our b binomial axis. Right, so let's apply the equations of equilibrium in the b-axis. So we're going to say summation of forces in the b going up in our reference positive, and we don't expect any movement in that direction. This is just going to be equal to 0, and therefore we have n minus w equal to 0, and our n is just going to be equal to mg, which is just equal to 5 times 9.81, and our motion is going to choose this direction, and this is our MAN. Alright, then we have summation of forces in the n axis, and this is equal to MAN, and going in this direction is our reference positive, right? And our AN is just equal to B squared divided by rho, and where our what is the question here is the radius, right? Our V is 8 meters per second, and our rho, which is the radius of curvature, is what we are looking for. Okay, so here what do we have? So we have Fs is equal to MAN. Fs we said is just 0.7 n, right? That's what we said, 0.7 n, and our n, we calculated n is 5 by 9.81, and this is just equal to m, and m is 5 times 8 squared divided by rho. Right, making rho subject to the formula, which is going to just be equal to 5 by 8 squared divided by 0.7 by 5 by 9.81, and therefore our rho will just be equal to 5 by 8 squared, okay, divided by 0.7 by 5 by 9.81. This gives us 9 point 9.32 meters, right? So this is the smallest radius. This is the smallest. Okay, I think this is about it. We have found rho, which is the radius of curvature, which is the smallest in this case. And I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye. and I'll see you in my next screencast.